Good evening, everybody. I am Vibhu Swain from Power Tech Consultant. Today, we shall start our webinar number 35. Let me share my screen with you. Now, in this webinar number 35, we shall discuss the remaining portion of energy conservation measures in furnace. That is basically chapter number 4 of book 2, that is energy efficiency in thermal utilities. We have already discussed around 6 number of energy conservation measures in furnace. Today we shall discuss the remaining 4-5 energy conservation measures. As an energy auditor, we all have to know these energy saving measures in furnace. Now, the 7th one is basically waste heat recovery from furnace flue gas. As I told you, furnace operates at a very high temperature, normally at around 1000 degrees centigrade, due to which the hot flue gas goes out and it takes enough of heat contained in the furnace as dry flue gas loss. So almost there is a sensible heat loss of 35 to 55% in the flue gas loss. So if the quantum of excess air flue gas temperature is high, then this loss will be there. But what we can do, we can recover that waste heat by employing certain waste heat recovery measures. There are a lot of waste heat recovery measures are available, and by that we can minimize the losses and we can increase some fuel saving. So the waste heat deployment of waste heat technology and availability of waste heat depends upon the quantum of excess air, flue gas temperature, and what we can do by getting some wet heat, we have to utilize in some of the heat requirement applications. So what are those? We can charge the stock. We can preheat the stock or charge. We can preheat the combustion air. Also, we can utilize the waste heat for power generations or steam productions and hot water productions. So these are the various options available, like preheating of stock, preheating of combustion air, or generation of steam or hot water. So this is the basically a picture. So this is our burner. The waste gas is going through the chimney, but we have deployed a waste recovery devices here. So whatever the heat we are recovering, that can be utilized to preheat the air or preheat the stock while it is going toward the furnace, or for any other processes like waste heat recovery boiler or to generate steam and hot water. Now, basically, how we charge the preheating? Now, when the raw materials are preheated by exhaust gas before it is being placed in the heating furnace, the amount of fuel necessary to heat them in the furnace is reduced because the stock will be heated up. Now, if I increase the temperature of the initial charging of the stock or initial stock, what will happen? The temperature will go up from room temperature to certain temperatures. So it will require less amount of fuel, due to which the fuel consumption rate will go down. That is one option. Second option is, now we have to add certain amount of air or oxygen into the combustion burner, so that by getting the fuel, what will happen? The combustion air will help the burning. Now, if you can heat the combustion air, then automatically the temperature of combustion air will go up and it will take less amount of fuel. So another one is basically, earlier preheating of combustion air using heat was common for large boilers, metal heating furnace, and high temperature kilns. But right now, we are utilizing this method for compact boilers as well as compact industrial furnaces. Now, the energy contained in the exhaust gas particularly can be recycled by using it to the preheat the combustion air. So if we can utilize the energy of the exhaust gas to preheat the combustion air, then your efficiency will also improve. These are basically known as recuperators. So recuperators is what? There are various type of recuperators. One is external recuperators. Another one is self-recuperating burners, modern recuperators. Now, if the furnace exhaust gas temperature is 1000 degrees centigrade, then modern recuperator can be utilized to preheat the combustion air to over 500 degrees Celsius. That means this results a saving of almost 30%. Now, this is an example of preheating the air for combustion by a recuperator. So, where is the recuperator? This one is my recuperator. What happens? This is the combustion air fan. Now, side is the furnace. This is the furnace one. Now, based on certain control technology, DCS or PLC control based, I am able to control this valve. So these valves are being controlled by the control panel. So what is happening? I need to put cold air to the burner. But if I put this cold air in the recuperators, what will happen? The hot gas is coming in this and going out. So the recuperator, this cold air will be heated up by utilizing the waste heat of the flue gas, and the hot combustion air will come like this and it will go to the fed to the burner like this and this. So this is my gas supply. This orange line is my gas supply, and this is my hot air supply, and this is my cold air supply. But cold air is supplied to the waste heat recovery devices, which is the recuperator here, and it is heated up by utilizing the heat of the exhaust flue gas. Now, these are external recuperators. So there are two types of external recuperators. One is radiation recuperators, and another is convection recuperators. Particularly, what happened in radiation recuperators? These are basically concentrating cylinders like this. This is a hollow pipe, and above this pipe, another pipe is there. So basically, there are two cylinders here. So one is meant for the cold air to pass like this, and another one is basically hot gas, flue gas pass. So the hot gas come like this, goes like this, and this cold air circulates in the annular positions and it goes out. So from the concentric cylinder in which combustion air passes to the annulus. Sometimes the combustion air, that means the air is supposed to be burned. There is a cold air. Annular space means which that is the space between two rings, or that is the space between two cylinders. So middle the internal space available between two cylinders is known as annulus. Now here the cold air pass and the exhaust air gas pass to the center. So what is happening? Because of radiations, this hot gas radiate heat to the cold air, due to which the temperature of the cold air goes up. So this is an example of radiation recuperators. Sometimes it can be, so it is suitable, it is simple in constructions, it is can be utilized with dirty gas, means where dust particle will be there will be some sulfur particle, it will be good with dirty gas, and it will have negligible resistance to flow. And if you have some space constraint, or you can replace the flue duct or the chimney by utilizing this radiation recuperators. So even if the space is limited, you can utilize this radiation recuperators. Now sometimes it can be reverse also, and it should be not be employed with the exhaust gases at less than about 800 degrees Celsius. So normally, if it is employed for exhaust gas temperature above 800 degrees Celsius. So this is a double cell radiation recuperator. Now convection recuperator. In this case, what happens? It consists of bundles of drawn or cast tubes. These are basically tubes. These are drawn or cast tubes. Now there are internal and external fins. Why fins are required? Fins are required because the heat can be radiated or heat transfer will be very rapid. So what is happening? So fins are there in the tube. Now these tubes are welded together in the air path. So this is my incoming combustion air. It goes like this, and there is a separator here, or it goes like this, come like this, and goes like this, or sometimes it goes full, then there is a separator here, then it goes out. So any type of designs are possible based on the temperature, based on the temperature profile, based on the quality of flue gas. That means air should come in, get heated up with the waste gas, and to have maximum surface area contact so that maximum heat transfer will occur. So we have divided this flow of air into various parts in the tubes so that rapid heat transfer will take place and the temperature will be improved with short time. Now basically the combustion normally pass through the tubes and exhaust gas outside the tubes. It has separate designs also like U2 design, double pass systems. So based on the different type of design, you can have based on the different type of requirement, we can have different type of designs. In certain application, it can be reversed. That means the waste gas can come like this, go out, and the combustion air can go in like this. So it depends the quality of gas, how you want to clean it, what is the area available in the furnace. So based on this design can be changed. Now these convection recuperators are more suitable for exhaust gas temperature of less than 900 degrees Celsius. So this is a temperature applications, and these are the two different type of convection recuperator, and another one is radiation recuperator. Then the another one is self recuperating burners. In this case, what is happening basically? This is a burner. Now natural gas is flowing like this. There is a ignition in which it is burnt. Now the combustion product, natural gas plus oxygen, it goes taken out to the furnace. So this is basically a burner. So what we have to supply here? We have to supply combustion air. Now see, now your waste flue gas is coming like this. Now from the furnace exit, you take out the hot combustion products and pass through like this, and you see there is the surface area contacts. These combustion air and this hot combustion product does not come physically contact into each other. They don't mix each other. But yes, this is in a separate path or separate pipe or separate vessels. This is another in a separate vessels. But both are interlinked so that the heat transfer will be very rapid. In this case, this goes like this goes like this, it goes like this, and it goes to the combustion air. But this hot combustion product goes like this again in this cylinder. It goes and it goes to the chimney or outlet or to the atmosphere. So they don't get mix each other, but they are interlinked so that maximum heat transfer occurs. Now, based on traditional heat recovery technique, the products of combustion are drawn through a concentric tube recuperator around the burner body and used for preheat the combustion air. Now, the major advantage of this type is it can be retrofitted to existing furnace structure to increase production capacity, without altering the existing exhaust gas ducting arrangement. Now, SRV are more suitable to heat treatment furnace where exhaust gas temperature are lower and there are no stock recuperation facilities. So these are basically suited for low temperature application or low temperature or heat treatment furnace. So we studied three types of recuperators. Now, when you do certain recuperator activities or take or save some waste heat, what will happen? Definitely there will be some fuel saving. So what is the formula to calculate the fuel saving due to recuperations? This is given by S is equal to P by F plus P minus Q. You have to remember this formula. What is S here? S here basically the fuel rate. That means S is your fuel saving rate. What is F? F is calorific value of the fuel, that is in kilocalorie per kg, is quantity of heat brought in by preheated air. That is also in kilocalorie per kg of fuel. What is quantity of heat brought in by preheated air? This is basically the ms d theta. So if you know the difference in temperature, specific heat of the air and mass of the air, then only you can calculate quantity of heat which has been taken by the preheated air. Then Q is quantity of heat taken away by exhaust gas. So based on the temperature which the exhaust gas is taking, based on that, that is also can be calculated by ms d theta or mass specific heat and delta T, and you can find out what is the fuel saving rate. You have to remember this formula. Sometimes these values will be given. You have to find out the fuel saving rate, or you have to find out the financial saving rate if fuel cost is given. Now, what is the disadvantage of recuperator? The disadvantage is that whenever these are additional path is given, recuperator is a basically metallic device. So because which the draft or the exhaust gas through a recuperator, it draft resistance causes a pressure loss. So there is a increase in path of the dry flue gas, due to which there is a pressure loss of 5 to 10 mm of H2O. And therefore you need to check the draft of the stack or chimney to take corrective measure for this pressure loss. Similarly, air blower for the combustion air. While the air for combustion goes through a recuperator, usually 100 to 200 mm H2O pressure is lost. Thus, discharge pressure of air blower should also be checked and necessary pressure should be provided by burners. So, because in case of burner also there is a pressure loss, these are the two things which are to be checked while installing a recuperator. Recuperator is a very good business, particularly thermal energy saving is concerned. So any auditor or any manufacturer or any future entrepreneur can take up the recuperator business. Will give lot of savings. Now you see here preheated. Now fuel conversion rate when oil is used. Now if the temperature is 1200 degrees centigrade or 1000 degrees centigrade, let us say these curves are different for different temperatures. That is the exhaust gas inlet temperature. So for different exhaust flue gas temperature, the fuel conservation rate will be different. For 1000 degree, almost if your preheated air temperature is, let us say 600 degree, that means you can save almost 35% of the fuel, which is a good saving. Similarly, this is the fuel consumption rate when natural gas is used. You see 1000. Now my temperature is, let us say 600, then or 500. I am saving almost 25% of the fuel. So in case of natural gas, the fuel saving conservation rate is little bit lower as compared to the fuel conservation rate of oil. But 25 or 30% fuel saving is a very good saving. So for which recuperator is a good business or good option for energy saving and energy conservation. Now another one is utilizing waste heat as a heat source for other processes. That means if the temperature of the heating furnace is in the range of 400 to 600 degrees Celsius, by taking the heat from the through air preheating or for combustion charge preheating, even if after that the temperature of the exhaust flue gas that is has come down to from 1000 degrees Celsius to let us say 400 to 600 degrees centigrades. Now this is also a good temperature in which it can be utilized to heat the steam or hot water so that it can be utilized in the process requirement. Now there will be reduction in fuel consumption based on the quantity of exhaust gas available and temperature range and operation time. Now sometimes you remember exhaust gas from the quenching furnace. This is one type of quenching furnace was used as a heat source in the tempering furnace because to avoid the need of fuel for the tempering furnace itself. So quenching furnace exhaust can be utilized in tempering furnace heat source. Now next is minimizing wall loss. Now as we have also discussed, furnace wall will be consisted of very thick materials like refractories, then the metal lining, then the coating. So these basically due to which the temperature inside the furnace is around 1000 degrees Celsius. Now it goes, the outside temperature is ambient temperature. Now because of the ceramics and everything, the because of the conduction radiation, the outside wall temperature of the furnace goes, let us say, to 70 or 100 degrees Celsius. Now there is a wind flow, so automatically some heat loss will happen on the external surface of the furnace. Now to have a steady state, when there is a heat loss, again more amount of heat will flow to the external surface if the wind velocity is there and the furnace outside is cooled by normal air ventilations. So some heat loss will be there. That is basically known as wall loss. So what we can do, avoid or minimize wall loss? We can do that by using good selection of refractories or insulation materials. Now the extent of wall loss depends upon various factors: emissivity of wall, thermal conductivity of refractories, wall thickness, whether furnace is operated continuously or intermittently. So these are the major factors on which the wall loss depends. Now prevention of radiation heat loss from the surface of furnace. How we can do that? Basically, this is the formula. Now, the quantity of heat released from the surface of furnace body is the sum of natural convection and thermal addition. So, by two way, the heat from the surface of the furnace can go or can be lost. That is one due to convection, that means due to flow of air in the vicinity of the external surface of the furnace, and another in the thermal radiations. Now, what is the total loss? Total loss will be in the reheating furnace can be calculated by adding the convection loss and radiation loss. So what are the formula? Q is the total heat release from a reheating furnace is equal to H, basically a factor, T1 minus T2 to the power 5 by 4, 4.88 E emissivity factor of the external wall, T1 plus 273 by 100 to the power 4 minus T2 plus 273 by 100 to the power 4. Remember, this is T1 is in degrees Celsius. We are adding 273 to get it convert it to Kelvin. You know, this your radiation loss is proportional to the square of 4 times or quadruple of the temperature or Kelvin temperature. Now, this is basically the convection loss. So, what is A? A is basically a factor. For ceiling, it is 2.8. For side wall, it is 2.2. For hearth or bottom of the furnace, it is 1.5. Now, T1 is the temperature of the external wall surface of the furnace. T2 is the temperature of the air around the furnace. That is basically the ambient temperature. E is the emissivity of external wall surface of the furnace. Now, let us find out this solve this problem. Now average surface temperature is 80 degrees Celsius. So what is given? T1 is given 80. Now what is ambient temperature? You can assume if it is not given, so ambient temperature is 30. So T2 is 30. The surface area is 20. So what is the heat loss from the what is given? Ceiling. So for ceiling, what is the what is the for ceiling? It is 2.8. A is 2.8. So 2.8, 80 minus 30 is the convection loss per kilocalorie per hour per meter square, and radiation loss will be 4.88 E. E factor is not known, but if you have studied the emissivity of heating furnace at the metal surface is around 0.75, you can remember it, or this data need to be given in the problem. So by multiplying this and 80 and 30, we can find out 632 kilocalorie per hour per meter square of heat loss is happening in the reheating furnace. Now he is asking what is the total list. So surface area is given 20 meter square. So by multiplying that, we can find out total heat loss is 12640 kilocalorie per hour. Now what is a ceramic fiber? Ceramic fiber is a low thermal mass refractory used in hot phase of the furnace fastened to the refractory wall. Now it has low thermal mass. Because of this low thermal mass, ceramic fiber, what is happened? The storage loss are minimized. That means it, because of its low thermal mass, it does not absorb much of the heat. So when it does not absorb much of the heat, the so the furnace storage loss, that means, are minimum. Now this has resulted in faster heating of the furnace and also for faster cooling. Now energy saving by this application is possible only in intermittent furnace. Let us find out example that intermittent furnace, that furnace which does not operate continuously. So let us say it is heated up, then it is operated, then after that it is cooled, or it is the operation is stopped. Now since during heating up or during operation some amount of heat has been soaked by the refractories by the metal, so what will happen? That heat or the stored heat will be lost when the furnace is not in operations, because it is an intermittent furnace. Now if it has a low thermal mass, that means this ceramic fiber will not absorb much heat initially, so, so storage loss will be low, and it also not release that much of heat, or so it is a faster heating of the furnace and faster cooling as well. Now ceramic coatings are basically, it promotes rapid and efficient transfer of heat, uniform heating, extended life of refractories. Now, emissivity of conventional refractories decreases with increasing temperature, whereas for ceramic coating it increases. Now, basically the ceramic coating can be applied in metal, can be applied in refractory, but typically its properties will be have to different. Ceramic coatings are non-toxic, non-inflammable, water-based. Now, this can be applied at room temperature, sprayed, or air dried. So, whenever your furnace is down, it is under maintenance or it is under shutdown or some breakdown work is going on. So, as an mechanical engineer or an energy professional, what we can do, we can apply ceramic coating. So, what will happen? The it will some kind of painting. Now, because its emissivity increases in temperature, emissivity of the ceramic coating increases as the temperature increases. So what will happen? So inside the furnace, if the temperature is high, it will try to emit that heat towards the furnace. So it will not allow the heat to get through the wall of the furnace to the outside. So this high good emissivity properties of the ceramic coating it utilized to save energy. So almost 8 to 20% of energy saving can be achieved using ceramic coatings. So ceramic coating is also a good example for energy saving and can be tried in your different plant to save energy. Now let us come to fishbone diagram. We have studied lot of diagrams, Sankey diagram, then then different process flow diagram. So let us understand what is fishbone diagram. This is nothing but a diagram to show what are the energy conservation analysis are available or options are available in furnace. So whatever we have discussed so far, all are put together. So this is basically the fuel flow. Let us find an example. This is a basically characteristic diagram of energy conservation for a reheating furnace. So how you can save energy? So these are the options to save energy. These are the 5 major options. One is combustion control, another one is basically waste heat recovery, recovery of waste heat, another one is good quality of equipment, operation, installations. So these are the major parameters through which your energy can be conserved in a furnace. Now, still there are certain other parameters, let us say for combustion control, what you require? Good quality of burner, so suitable capacity, suitable oil pressure, suitable oil temperature. Another one, damper. The furnace draft should be good. Oxygen analysis. If oxygen analysis is carried out, then excess air can be controlled. So these are the 3 parameters basically for to control the combustion. Now, also furnace pressures, air ratio control are part of this combustion control. Waste heat recovery, recuperator, waste heat boiler, preheating the materials, are the 3 options are available for waste heat recovery boiler. Equipment, improved gas flows, position of the burner, maintenance of the burner, type of burner, or extension of preheating zones. So these are the equipment related energy conservation measures. In insulation, skid pipe, double insulation, furnace wall, lightweight insulation material, ceramic coatings can come together. Now, operation, improved heat pattern, good loading, rate of operation, dropping of charging, discharging temperature, material arrangement, charging, hot charge, operation. So these are operational ways by which you can save energy. Now, since this look like a fishbone, so therefore these options are also called as fishbone diagram. Now let us try to solve this example. An oil-fired preheating furnace has an operating temperature of 1000 degrees Celsius. Average furnace oil consumption is 440 liter per hour. So oil consumption is given. Flue gas exit temperature is 300 degrees Celsius after the air preheater. That means it is the after air preheaters. Combustion air is preheated from ambient is given 35. So combustion air is heated up to 200 degrees Celsius. These temperature parameters are important. Now, specific gravity of oil, you know, 0.92. Calorific yield is 10,200. O2 has been measured in the flue gas. This is 14%. Why it is required? To calculate the excess air. So theoretical air is given authorized. You have to remember that for oil, for 1 kg of oil, you require almost 14 kg of air. Specific heat of the air, you can also remember it is 0.24. Specific heat of flue gas, you can also remember it is 0.23, but in this case, it has been given. We have to find out sensible heat carried out by the exhaust gas and heat recovered by the combustion air in kilocalorie as a percentage of energy input. So how to find out? Now let us find out first what is the energy input. Energy input, we have to understand what the flow rate, calorific value, and it is in liter per hour, calorific value in kg, kilocalorie per kg. So what we have to convert liter into kg per hour by multiplying specific gravity. Specific gravity is 92, so 440.92 into GCV 10,200. So that means energy input is 41,28960 kilocalorie per hour. O2 is given 14. So what is excess air formula? O2 by 21 minus O2. So it becomes 200%. That means it is supplying 200% of excess air into the furnace. But what is the theoretical air requirement? You know, 14 kg of air is required for 1 kg of oil. So actually, how much of air is being supplied? It is not 14 kg. It is almost 200% above 14 kg. So 14 into 1 plus 200%. It is that means almost 42 kg of air is supplied for kg of oil, because it is 200% higher. Now from this we can find out what is the actual mass of the air supplied. Now what is the actual mass of the flue gas? This is the air. Flue gas will be fuel. Fuel has to be added. So what is the fuel? Fuel is 1 kg, because we are all are calculating per kg basis of oil. So fuel is 1 kg, 42 is the excess air. So what is the total mass of the flue gas? It is 43 kg per kg of oil. Now you know specific heat 0.23. Now delta T is of the flue gas. Flue gas is has been heated from 35 to 300 degrees Celsius, because ambient is 35, 300 is the exit temperature given data. So 265 is the delta T. So what is the heat loss in combustion, or sorry, flue gas loss? 43 is the total dry flue gas or mass of flue gas. 0.23 the specific heat. Then 300 minus 35, it becomes 1060920 kilocalorie per hour. So sensible heat loss in the flue gas will be percentage of heat loss to input energy. So this divided by this one, energy input, is the percentage of the heat loss in the flue gas. This is almost 25.7%, which is a very huge amount. Now out of this, how much or what is the heat gained by the combustion air? 42 into 0.24 into 200 by 35. Why 42? Because why 42? Because 42 of actual mass of air is being supplied. So 42 and 0.24. Why 0.24? Because that is the specific heat of the air. So 200 minus 35. 200 is the temperature. It is also given here. 200 is the air fitting final temperature. So by doing this, we can find out heat gained by combustion air is almost 67263. So what is the heat gained by the combustion air? Just divide it, which almost 16.3%. So from this furnace, we are able to save 16.3% of the saving because of the preheater, air preheater. So air preheater also is like an recuperator, plays an important role in conserving furnace loss or to increase the furnace efficiency. With this, I close this chapter number 4 of book 2. In the next class, we shall study the numericals related to furnace, which is basically book 4. So book 4, those who are applying can go through that content, and by solving some numerical, it will be easier for everybody to understand the furnace efficiency, furnace calculations, and other parameter of furnace. With this, I close. Good night. Thank you.